Hello and welcome to the e-learning package on the transformation of graphs. This is part 2 of the 3-part package on scaling. Please look at example 11 from your lecture notes. In your graphing calculator, please key in the graphs of y is equal to x squared minus 1, y is equal to a half of x squared minus 1, and y is equal to 3 times x squared minus 1. What do you notice about these curves? After you've keyed them into your graphing calculator, you should have something that looks sort of like this, where the blue curve is y is equal to a half x squared minus 1, the black curve is y is equal to x squared minus 1, and the red curve is y is equal to x squared, 3 times x squared minus 1. What do these graphs look like? They all look kind of similar, but the graph of 3 times x squared minus 1 has been stretched out along the y-axis, whereas the graph of a half x squared minus 1 has been compressed along the y-axis. That is, the graph of y, so what we call this type of pattern a scaling, and we say that the graph of y is equal to a half times x squared minus 1 is obtained by scaling our original curve, y equals to x squared minus 1, by a scale factor of 1/2 parallel to the y-axis. We say that the graph of y is equal to 3 times x squared minus 1 is obtained by scaling the original graph, y equals to x squared minus 1, by scale factor 3 parallel to the y-axis. This can be generalized as the following. For a positive constant a, y is equal to a times our function is obtained by scaling the graph of the original function parallel to the y-axis with a scale factor of a. So that is, if I have y is equal to 2 times x squared, this is going to look like y is equal to x squared scaled parallel to the y-axis with scale factor 2. Why is this the case? Well, let's look at a curve. This can be my curve, y is equal to f of x. This point on the curve is going to be x, f of x. But I now want to multiply it by some positive constant. So what does that do? It changes this distance. So if this distance was originally, say, 1 unit, so this would make f of x negative 1, and I now want to look at y is equal to 2 times f of x, what's going to happen? This distance here is going to go down to here. It will become 2, because my x coordinate's the same, but my y coordinate has now doubled its value. It's now 2 times f of x. What about for a positive point? Well, again, let's suppose this distance was 1. What happens if I was to scale it? It would double. It would go up here. This is where x 2 times f of x would be. And so my graph will now look very stretched out. It will still have the same roots. It will still cut in the same place, but it's going to be a stretched out version of my previous graph. Let's take a look at example 12. Sketch these 3 graphs into your graphic calculator. Y is equal to x plus 2, x take 2. Y is equal to a half x plus 2, and a half x take 2. And y is equal to 3x plus 2, 3x take 2. What do you notice about these curves? If you look at these 3 curves, what do you see? This red one is the curve of y is equal to 3x plus 2, 3x take 2. The black curve is our original curve, and the blue curve is the curve y is equal to a half x take 2, and a half x plus 2. What has happened here? Where I've replaced x by a half x, my curve has now been stretched out along the x-axis, and where I've replaced it with 3x, it's now being compressed along the x-axis. You can see that the y-axis remains invariant throughout this. So I haven't seen any change in y. What do we say? We say that the graph of y is equal to a half x take 2, a half x plus 2, is obtained by scaling the curve, our original curve, y is equal to x take 2, x plus 2, by scale factor 2 parallel to the x-axis. So where this point was 2, this point is now 4. Where this point was now slightly bigger than 1, this point's now slightly bigger than 2. Right? What about the red curve? We can say that the graph of y is equal to 3x take 2, 3x plus 2, is obtained by scaling our original curve, y is equal to x take 2, x plus 2, by scale factor of a third parallel to the x-axis. So if we look here, we had a turning point between 2 and 3. That turning point is now less than 1. Where this cuts, where we had a turning point just above 1, this cuts at about a third. Where I've cut the axis at -2, this now cuts at about -2/3. So we can see that we've scaled it by a factor that's less than 1 because it's become smaller, it's become compressed, and it turns out the scale factor is 1/3. This rule can be generalized. So if I have a positive constant a, then the function y is equal to f of a times x can be obtained by scaling the graph, our original graph of y is equal to f of x, parallel to the x-axis with a scale factor of 1/a. In particular, this means if a is between 0 and 1, so if a is a fraction, then this will make our graph bigger, or stretch it out wider. It'll stretch it out along the x-axis. And if a is bigger than 1, it compresses the graph. Why is this the case? Well, again, we've got to follow a point when we do this. So let's take a look at something like this, right? This is my original curve, y is equal to f of x. And let's say I want y is equal to f of 2x. Well, let's say this is the point 2, 0, and I want to find the graph y is equal to f of 2x, right? Well, when x equals to 1, what's this going to be? Then I'm going to get f of 2 times 1, so f of 2 here, right? But from here I can see f of 2 is going to be 0. So it's going to move forward my new curve, right? It will intersect twice as early as it would have otherwise. The axis is still the same, but everything else will be happening twice as quickly. So it would look something like that. It would be a compressed version of my original graph. What have we covered in this package? We've talked about scaling vertically, which is where I have y is equal to a times f of x. And we've talked about horizontal scaling, where y is equal to f of a times x. To test your thinking, please have a go at this question. You may now proceed on to the final part of this e-learning package.